In this lesson, we're going to be graphing tangent functions. We're going to graph one period of each of the following, and for each graph, we're going to answer the following questions. We're going to state the domain, give the range. We're also going to state where the period begins and ends. That's with the x values. We're also going to be talking about the length of the period, and we're going to come up with an equation that represents all the vertical asymptotes for these tangent functions. Our approach to graphing is somewhat different than it was for sine and cosine. Because we have vertical asymptotes for the tangent and cotangent graphs, our approach needs to be a little bit different. So this is how we're going to do it. Okay, so put yourself a little note up here. We're going to set bx minus c equal to negative pi over 2. And we're going to set bx minus c equal to positive pi over 2. Now remember, we're graphing tangent functions, so the reason I choose negative pi over 2 and positive pi over 2 is because the parent function for tangent has vertical asymptotes at these two x values. All right, once we do that and we begin to graph, then we're going to go back and we're going to adjust the graph for any a and d values. Let me put adjust for a and d. All right, so our first example is y equals negative 2 times tangent x. And just by a quick inspection, we can see that the negative is going to have the effect of a reflection, and 2 is a, and so our a is negative 2, but the amplitude, I guess, if you want to say it, this 2 has the effect of vertically stretching the tangent graph. So those little graphs of tangent will be a little bit more steep. Okay, let's go ahead and come over here and state our a through d values. So a is negative 2, we see b is 1, and c and d are both 0. All right, so we're going to have these on hold because we do have to come back and adjust for a and d. Okay, these right here we won't need to worry about because these will be taken care of, b and c, when we actually set bx minus c equal to negative pi over 2 and bx minus c equal to positive pi over 2. All right, so the first thing we're going to do for a tangent graph is we're going to look in the new equation and we're going to find bx minus c. Well, in the structure of bx minus c, okay, we can see that bx minus c would represent the angle. Well, so the only thing I have for bx minus c is just x. And if we think about that, that's really just 1x minus 0, where b is 1 and c is 0. So bx minus c is really just going to be this angle that follows after the tangent function. All right, so this is how we'll start. We'll say, okay, well, bx minus c, which is just really x, we're going to set, so bx minus c, which is really x, because we don't have b is 1 and c is 0, we're going to set bx minus c equal to negative pi over 2. And then we're also going to set that same x equal to positive pi over 2. For this first example, we can see that we don't have to do any simplifying here because x is already by itself. So what that informs us is that for this graph right here, the vertical asymptotes for this new graph will be the same as they are for the parent function. There's been no adjustment to the vertical asymptote because there's no b value, well, the b value is 1 and c is 0. All right, at this point, I'm going to go ahead and sketch these vertical asymptotes on my grid. So we'll let that be the y as the x, and then we can decide how many tick marks will represent negative pi over 2. So I'll just choose 2 of them. So negative pi over 2 and then positive pi over 2. All right, so these are going to be our vertical asymptotes. So anytime we set bx minus c equal to either of these two values for tangent, these become our new vertical asymptotes. Well, they're actually the same as the parent function. So let's go ahead and sketch in, dash in these vertical asymptotes. Once we get the vertical asymptotes, we know what the tangent graph looks like, but what we want to do is come back and adjust for any a or d values. A is going to vertically stretch and possibly reflect, and d would shift the graph of the tangent function up or down. Well, since I don't have a d value, I just have to manage the negative 2. Well, remember, tangent kind of comes down like this, so with the reflection, it's going to actually come from this direction passes through the origin. Make sure you're bending it the right way and approaching the vertical asymptotes from the left and the right. You really can't see a vertical stretch of 2, so I wouldn't worry about that. I mean, we would be able to see a shift up or down, but the vertical stretch, it's just not going to be apparent on our sketch. All right, let's go ahead and answer the questions. I'm going to get the domain last because I always like to get it after I get the vertical asymptote. So let's start with the range. All real numbers. See where the period begins for this part of the graph that we're doing. So negative pi over 2 and ends at positive pi over 2. Even though these are vertical asymptotes, we're going to go ahead and put the equal signs there. All right, D says, what's the length of the period? Well, we can see that the length of the period is pi. Okay, the couple ways you can get pi. Okay, either by visually looking at it or subtracting pi over 2 minus negative pi over 2, which results in pi. Or, remember the formula for tangent and cotangent's period is not 2 pi, but just pi divided by b. In our problem, b is 1, so we would get pi. Probably the most difficult is going to be the vertical asymptotes. Not so much for this graph, but maybe later in some of our more complicated problems. So vertical asymptotes, okay, what we did was we had that condensed version to list all the vertical asymptotes. So common practice, let's start with the first positive vertical asymptote if I don't have one at x equals 0. So pi over 2 plus, and it's always an integer multiple of the period, so n pi. And once we get the equation that represents all the vertical asymptotes, we can go back and answer the domain question because the domain is going to be all real numbers except, that's what E stands for, x equals, and we just re-record the equation that represents the vertical asymptotes. And that's it. All right, example 2 is a tangent function. What do? Well, we don't have those formulas like we did for sine and cosine. So our strategy is to set bx minus c equal to negative pi over 2 and bx minus c equal to positive pi over 2. All right, I'm going to go ahead and state A. B is 3. There is no shift left or right, and there is no shift up or down. All right, I'm going to take bx minus c, but in this problem, bx minus c is 3x minus 0, so I just take the new angle, 3x, as opposed to just x here. I'm going to set 3x equal to negative pi over 2 and 3x equal to positive pi over 2. The reason we're setting them equal to these values again is because these are 2 of the vertical asymptotes for the parent function tangent. All right, well, the equations of the new vertical asymptotes will be what I get when I isolate x. So I'm not going to divide by 3 because that makes this complicated. Remember, our other option is to multiply by 1/3. And since I already have a fraction here, let's just multiply by 1/3. So 1/3 of 3 is just x. And then here, I'm going to get negative pi over 6. Multiply by 1/3 again over here, and we get positive pi over 6. So this b value has the effect of changing our vertical asymptotes, and we can see with these new values that those are not the vertical asymptotes of the parent function. As a matter of fact, these are smaller. If I were to look at this graph right here compared to what I did graph here, okay, this graph would be made horizontally thinner. It's a horizontal compression or a horizontal shrink. Might not show up because of the way we choose to graph it, but if we graphed this on a calculator and compared these two, this graph would certainly be a lot thinner and more compressed than this one right here. All right, so I set bx minus c equal to negative pi over 2 and positive pi over 2. I'm going to go ahead and put those vertical asymptotes on my graph. If you really want to kind of show that it's thin, you can decide, well, hey, I'll just let one tick mark be negative pi over 6 and positive pi over 6. You don't have to, you choose. Dash in your vertical asymptotes. Okay, and remember, we go back and adjust for any A or D values. Well, I don't have any vertical stretches or shrinks, no reflection because there's no negative, and I don't have to shift this graph from the origin up or down any because D is 0. So I have to go back and look at my parent function for tangent, and it looks like this. All right, we're going to state all these items over here. I start with the range. The period begins right after x equals negative pi over 6 and ends at right before x equals pi over 6. If I were trying to find the horizontal distance between these two consecutive vertical asymptotes, excuse me, this would be 2 pi over 6, which reduces to pi over 3. So you can eyeball it. You can take pi over 6, the greater value, pi over 6, and subtract a negative pi over 6. And that's going to result in 2 pi over 6 or pi over 3, or another option, use the formula. So take pi and divide it by 3, which is b, so we're going to get pi over 3. All right, what is an equation for all these vertical asymptotes? Well, we typically start with the first positive vertical asymptote if x equals 0. The y-axis is not an asymptote, so pi over 6 plus, we don't add n pi here because we want to think about where would the next vertical asymptote be? Well, the next vertical asymptote would be right over here, 2 blocks over. And what was this distance again right here? Well, it's pi over 3. So we're going to take the first positive vertical asymptote and add n times the period, n times pi over 3. All right, so this just tells us between consecutive asymptotes, we have a pi over 3 difference. And last, I would do part A. All reals except x equals the equation for the vertical asymptotes. All right, example 3, following the same strategy. Okay, all of this after the tangent function is your bx minus c. So a is 1. Notice that the coefficient on x is 1. So then I can state that c is positive pi over 2, and I don't have a shift up or down. All right, then let's come over here and let's state that x minus pi over 2, this is your bx minus c, is equal to negative pi over 2. And we want to do x minus pi over 2 is equal to positive pi over 2. So your bx minus c is always equal to negative pi over 2 and positive pi over 2 because we're dealing with tangent. When we deal with cotangent, we'll put 0 here and pi here when we're dealing with cotangent. All right, well, what do we have to do to isolate these x's to get our new vertical asymptotes? Well, I need to add a pi over 2 to both sides. So here I'm going to have x equals, well, actually 0, because I'm shifting these vertical asymptotes to the right pi over 2. Add a pi over 2 here. Well, a half pi plus a half pi is going to give us x equals pi. Let's come over here and put those asymptotes on our grid. All right, so x equals 0, can't really see it, but it is dashed along the y-axis, and pi. 1, 2, 3, 4. I guess I'll let 4 tick marks represent a distance of pi. You can use whatever you want. Okay, I've got the vertical asymptotes in place. What's next? We go back and we take a peek at A and D. Now B and C are already taken care of because that gave us our new vertical asymptotes. So there is no change as far as a vertical stretch or shrink. There is no reflection because A is 1 and we do not shift up the graph. So halfway between 0 and pi, I will have an x-intercept, and then I can draw my tangent graph to approach those new vertical asymptotes. All right, just like up here, what did we do? After stating the A through D values, we came up with the new vertical asymptotes. We sketched them. So B and C aren't really necessary because it's taken care of right up here, but we do have to go back and look and adjust for any A or D values. All right, let's finish filling in this information. I can quickly see that the distance between these two x values is pi, or I can also remember that the formula is pi divided by b. B is 1. All right, equations of the vertical asymptote. Well, the first positive vertical asymptote is pi, but remember we do have one at 0. So we usually start with that 0. We don't have to put 0. You could put 0, you could put pi here, whatever, plus n times the period. So the next vertical asymptote we'll have is at an integer multiple of pi. I'm not writing down that n is any integer. We're just going to assume because that's the work we've been doing. All right, so I could write down x equals just n pi, because if n is 0, I'm at 0. If n is 1, I'm at pi. If n is 2, I'm over here at 2 pi. If n is the integer -1, then I'm at negative pi. This formula seems to accurately represent all the asymptotes. Could you have done starting with pi? It doesn't matter which vertical asymptote you start with, but it does matter what you add as far as this expression. So I'm going to come up here and do all reals except x equals, and I'll just choose the shortest version, n pi. All right, we'll continue graphing tangent. All right, I know I'm going to vertically stretch tangent, but I'm not going to reflect it. X's coefficient is 1. That way, C is going to be negative pi over 3, always the opposite. And I don't think I have a shift up or down. All right, we're going to take bx minus c. Set it equal to negative pi over 2, and then also to positive pi over 2. All right, let's solve both of these equations for x. So it looks like we're going to have to do some fraction work here. Not a problem. Let's subtract pi over 3 to both sides. Cancel. X equals. All right, so what's negative pi over 2? I'm going to come over here. Negative pi over 2 minus pi over 3. Well, let's get 6 to be the common denominator. So if this is 6, then this has to be 3 pi over 6. If this denominator becomes 6, we have to multiply top and bottom by 2. All right, so negative 3 pi minus 2 pi is negative 5 pi over 6. All right, what's positive pi over 2 minus pi over 3? Well, I'll come back over here and go, well, if that wasn't negative pi over 2, it was positive, then I'd have 3 pi over 6 minus 2 pi over 6. So this right vertical asymptote is going to be positive pi over 6. Okay, so I see that I have more distance from the y-axis to the left than I do from the y-axis to the right, just because of these values. So I still think we'd be okay drawing our y-axis here. All right, from the y-axis, I've got to go left 5 pi over 6 sections, so probably each tick mark will be a pi over 6. So right here on the 5th one, I'm going to call that negative 5 pi over 6. And then to the right of the y-axis, that'll just be your 1 pi over 6. Dash those in. Okay, let's slip the tangent graph in between these two consecutive vertical asymptotes, but go back and make sure we've already taken care of this. This was our shift left pi over 3. We have a vertical stretch, but no shift up or down. So halfway between these two vertical asymptotes, I'm going to put the x-intercept. So 1, 2, 3, 4, 5, 6. So 3 in either direction, 1, 2, 3. So here's going to be our x-intercept because we're not shifting. We don't have a d value, just 0. And then tangent is going to go back this way. So it's a vertical stretch. So you can kind of suggest that the graph is, going to approach pi over 6. And then here, suggest that the graph is going to approach negative 5 pi over 6. But make it kind of thin, this graph, because that's what the effect of A does. It just vertically stretches it. It just takes a little longer for it to get really close to those vertical asymptotes. All right, range. Vertical asymptotes. Okay, if I subtract pi over 6 minus 5 pi over 6, I'm going to get pi. So my period is pi, or remember pi over b, but b was just 1. Okay, the vertical asymptote. So I see the first positive one is pi over 6 plus n times, always multiply by the period for tangent. Record the domain. All right, continuing with 5. Notice the arrangement here. This is actually your d value. B is 4. C is not negative pi over 4 until I factor that 4 out. Oh yeah, and A is 1. I think what I'm going to do here is I am going to rearrange. I'm going to put the tangent up front. I'm right here at the bx minus c, but I'm going to do a bracket because remember what we have to do is we have to factor out that 4. And then I'll put the plus 1 behind it to look like the d here. All right, so I'm concentrating on factoring out a 4 from this expression. So I know this will be x. I know this will be plus. What has to go right here so that when I multiply 4 into it, I get pi over 4? Another way to think about it is, what is pi over 4 divided by 4? So pi over 4 divided by 4 means keep, change, flip. So that'd be times 1/4. This has to be pi over 16. Let's double check our factoring. So if I multiplied the 4 back in, yes, I get to 4x. If I multiplied the 4 into the pi over 16, I would get 4 pi over 16, which does reduce to the pi over 4. All right, so A is 1, B is 4, C is negative pi over 16, and D is 1. Really, we don't need the B and the C values because we're just going to come back and make adjustments for A and D because the B and C values are all wrapped up in what we do up here when we set bx minus c equal to the negative pi over 2 and positive pi over 2. All right, so now to do these formulas, I'm not going to look at the factored version because I would have to just undo what I did. I always go back and look at what falls after tangent before I factored it out. So let's do 4x plus pi over 4 equals negative pi over 2, etc. All right, it's going to take some work here. So, all right, let's solve for x. So first we subtract pi over 4. All right, so 4x equals negative pi over 2 minus pi over 4. Well, let's get a common denominator of 4. So that means if this becomes 4, multiply the top by 2. So we have negative 2 pi and a negative 1 pi. So this is negative 3 pi over 4. I need to divide by 4, but I'm not going to. Instead, I'm going to multiply by the reciprocal, 1/4. That'll take care of getting just x. So x is going to equal negative 3 pi over 16. Okay, let's work on this other vertical asymptote. So we'll subtract the pi over 4. Remember, if we come back over here to this work, if this is now a positive pi over 2, I will erase that just for my work here. I've got the common denominator, so 2 minus 1 pi is just 1 pi. So pi on top, 4 on bottom. Just working with fractions. Those cancel. That collects to here. All right, let's get x by itself. Let's not divide by 4. Let's make a wise choice and multiply by 1/4 since we already have a fraction over here. And we're going to get pi over 16. All right, so that took care of the b and the c. Let's go ahead and put these vertical asymptotes on our grid. All right, how do we want to scale this? Well, I think just kind of like in the previous example, I'll let each tick mark represent 1 pi over 16. So negative 1, negative 2, negative 3 pi over 16. Make sure and label these tick marks. So that means only one tick mark to the right of the y-axis will be our positive pi over 16. All right, all that's left is to make adjustments for A and D. Well, A, there's no reflection on tangent. There's no vertical stretch or shrink, since A is 1, but we do have to shift the graph up 1, all points on the tangent graph. So let's remind ourselves that halfway between these tick marks, 1, 2, 3, 4, 2 over from either side, we would typically have an x-intercept right here, but remember we have to shift this graph up 1. So take that x-intercept that would otherwise be there because of D and move it up 1. So off of this point, which is normally your x-intercept, this is how we're gonna like draw part of the graph, kind of concave up, and then off this point that's not on the x-axis, we'll continue downward. All right, so what is the period? Well, what's pi over 16 minus negative 3 pi over 16? Well, that'd be 4 pi over 16 or pi over 4. What's another way we can get it? By reading it from the graph, or remember, take pi and divide it by b, and b was 4. The equations of the vertical asymptote, I'm going to start with pi over 16. And I'm going to add n times my period, n pi over 4. Consecutive vertical asymptotes are separated by a pi over 4 distance horizontally. All right, and our last example, I start by listing all my A through D values. So A is 3, B is 1. I don't have to factor anything out like the previous example, so B is 1. C is negative 2 pi, and we do not have a shift up or down. So I don't need to factor anything out here because B is 1. The reason I did here is because I needed to see what C was to accurately reflect it if I'm going to record it. It might have had to been negative pi over 16. It almost looks like I forgot the 1. Yeah, I think that should have been negative pi over 16. I think I left off that little 1. Okay, so what do we do? Now we come over here for tangent, and it'll be the same for cotangent. It's just that we'll set bx minus c equal to 0 and pi because those are the parent function vertical asymptotes that we usually represent. All right, so bx minus c is this value. So x plus 2 pi, etc. So how about if we make this positive? All right, let's subtract 2 pi from both sides. All right. Some of you guys are real good at your mental math, so you know negative 2 and negative 1/2 is negative 5/2. But if we need to come over here and do the little work, that's fine. So I'm going to do negative pi over 2 minus 2 pi. Common denominator would be 2, so this will be 4 pi over 2. So negative 1 and negative 4 make negative 5 pi over 2, just as we thought. All right, well, what happens when we adjust to make this negative pi over 2 positive pi over 2? Well, then we've got 1 whole minus 4, so that's negative 3 pi over 2. Notice that both our vertical asymptotes are negative, and that makes sense because we're shifting the graph of tangent left 2 pi. All right. I think I'll just keep the y-axis where it is on the grid. We've got to go to negative 3 pi over 2 and then negative 5 pi over 2. So, I think I'll just call this negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2. 4 and then 5 would be right here. Maybe I could have used 2 tick marks for each pi over 2, but that's okay. Okay. All right, and then we look back at A and D. We don't shift up or down, but I do vertically stretch by 3. There is no reflection. Halfway between, I'd put the x-intercept. I don't move that point up or down because D is 0, and it's going to be real thin anyway. Something like that. And maybe I should have moved that y-axis over here so I could have kind of spread this out, but that's okay. All right, let's come down here and record this information. All right, the smaller vertical asymptote is typically listed first. All right, and what's the difference between these two? Well, we can see that there's a 2 pi over 2 difference in here. Oh, that's really small. Okay, I could take the bigger x if I want to find the period length for part D. Remember, these are our options. Take the bigger x and subtract what was before it, which means change that to positive, and this would be 2 pi over 2 or just pi. So the period is pi, or remember the formula is pi divided by b, and b was 1. All right, so typically we've had a positive vertical asymptote to work with, but that's okay. I'm just going to choose one of these 2 vertical asymptotes. It doesn't matter which one. I'll just choose the negative 3 pi over 2 because it's bigger. I know it's not positive, and that's okay. Plus, and then always n times the period for tangent. Okay, well, hopefully after these 6 examples, you're a little more comfortable with graphing the tangent functions, and now it's just time to practice.